The whole sky has this faint, cold glow. That's the cosmic microwave background. It's the oldest light we can see. It's like a fossilized photograph, but from when the universe was just 380,000 years old. That light has been traveling for over 13 billion years, and it carries secrets, the encoded secrets of how the cosmos began. You can learn to read it. To read that celestial relic, to understand what reality is made of, its ultimate ingredients, you can see what invisible forces were at work, how they sculpted everything from that smooth beginning. And maybe the light holds hints of other universes, what it's like to look at that, to see the first chapter of everything. To really see that first photograph, you need to get the moment it was taken. For almost 400,000 years, the whole cosmos wasn't something you could see through. It was this searing, churning fog, a plasma so dense and hot that light couldn't travel straight. A photon would be born and then immediately crash into a free electron, scattering, getting absorbed, trapped in this chaotic dance. The universe was a brilliant, opaque fireball. Glowing from within but completely impenetrable because there was no outside. Everything was inside this soup. Then it changed. The universe had been expanding, and as it expanded, it cooled. The temperature dropped over all those millennia until it hit a threshold, about 3,000 Kelvin. At that temperature, something became possible. The free electrons, which had been ricocheting, could finally be captured. They slowed just enough to be grabbed by atomic nuclei, mostly protons, to form the simplest atoms. Neutral hydrogen. This event is called recombination. It wasn't a recombination like they'd been together before. It was the first true marriage of these particles into stable, neutral things. And in that moment the fog lifted. With electrons bound into atoms, the roads cleared. The photons that had been trapped, bouncing endlessly, suddenly found no more free electrons to scatter off. They were set free. The universe for the first time became transparent. Light could travel in straight lines across vast distances. That sudden flash of liberation, that first unimpeded journey of trillions of photons, is what we detect now. We call it the surface of last scattering. It's not a surface like a balloon's skin. It's a moment frozen in time, a spherical shell at the edge of everything we can see. Every direction we look, our telescopes pick up light that began its journey from that exact epoch, from that final scattering. Think of it like the flash from a colossal explosion. But one that's been cooling and stretching for over 13 billion years. The brilliant white-hot light from that decoupling has been redshifted by the expansion of space. Stretched from visible warmth into the microwave part of the spectrum, cooled down to just 2.7 degrees above absolute zero. It's a cosmic afterglow. Faint and cold, but everywhere, and this is the truth. When we point our instruments at the sky and map this microwave background, we're not looking at stars or galaxies. Those came much later. We're looking directly at the newborn universe, at its moment of first transparency. It's a snapshot of cosmic infancy. The cosmologist George Smoot once reflected on this signal. He said it carries an almost overwhelming weight of meaning. This ancient glow is the canvas, a blank, smooth canvas of near-perfect uniformity. The canvas upon which every galaxy, every star, every structure we see would eventually be painted. But if you look closely at this canvas, you see it's not perfectly smooth, and those tiny imperfections, those faint whispers in the first light, hold the next secret. There was this constant static in their data, just this faint hum. Arno Penzias and Robert Wilson, they were using a bighorn antenna in New Jersey, trying to pick up radio signals from the galaxy. But there was always this noise. It was everywhere, all directions, all the time. They checked everything. They even cleaned out pigeon droppings from the antenna, thinking that was it. But the hum stayed. It wasn't a problem with the equipment, it was the universe. They'd found the cosmic microwave background, that microwave hiss about 3 degrees above absolute zero. It was the cooled down remnant from the beginning, from the hot, dense start of everything. That discovery got them the Nobel Prize. It was the first direct evidence for the Big Bang. Proof the universe started in fire, but the thing about this ancient light was how smooth it was. When we mapped the whole sky, the temperature was incredibly constant. 2.725 Kelvin, and from one part of the sky to another, billions of light years apart, the temperature only varies by a tiny, tiny amount. Less than a few parts in 100,000. It's almost perfectly uniform, and that created a puzzle, the horizon problem. The light we see from opposite sides of the sky, those regions were too far apart. Even light traveling at the speed limit wouldn't have had time to go between them and make their temperatures the same. So how did they coordinate? How did they end up exactly the same? Alan Guth had an idea, a solution. He proposed that in the first fraction of a second, the universe went through a period of exponential expansion. Cosmic inflation, space itself stretched faster than light. In that instant, a region smaller than a particle inflated to become larger than everything we can see today. And before that inflation, that tiny region had time to even out, to reach one temperature. Then inflation stretched that smooth patch to the size of the observable universe. It solved it. It explained the smooth sky, so that background is our foundation. It's the 0 point, like a perfectly calm, vast lake at dawn, serene. Featureless, but on that lake the tiniest ripples matter. Those minute variations in the temperature, those 1 part in 100,000 differences, they aren't mistakes. They're the seeds, they're the gravitational fingerprints of the first structures, the slight clumps where matter began to gather. And from those faint whispers in the first light, every galaxy, every star, everything we know would eventually grow. For a long time, that smooth cosmic canvas was just an idea. Then, in 1992, a satellite showed us the ripples. The Cosmic Background Explorer, COBE, had been looking into the cosmic static for years. It was trying to measure that faint glow with a precision no one had managed before, to see if the smoothness was really perfect, and what it found changed cosmology. It turned it from something speculative into a precise science. The data showed the ancient light wasn't perfectly uniform. There were these incredibly subtle variations in its temperature. Tiny hills and valleys in the energy, differences of about 1 part in 100,000. To put that in perspective, if the cosmic background were an ocean as smooth as a mirror, these ripples would be about the height of a sheet of paper compared to the depth of the sea. Finding them was like picking out one specific grain of sand on an endless, smooth beach. The lead scientist, George Smoot, announced it. He called it the handwriting of God. That was a poetic way of saying we were seeing the first fingerprints on creation, the primordial imprint of structure itself. These tiny temperature differences are called anisotropies. They aren't random noise, they're the magnified signatures of quantum fluctuations, those microscopic wrinkles in spacetime from when the universe was smaller than a proton. Cosmic inflation, that brief hyper-expansion, stretched those quantum seeds to astronomical sizes. What was once a quantum fuzz became the large-scale blueprint. And here's the crucial link. A slightly cooler spot on that map doesn't just mean less energy there. It marks a region that was slightly denser in the very early universe. Photons, particles of light trying to escape that denser region, had to climb out of a slightly deeper gravitational well. They lost a tiny bit of energy doing that, which we measure as a slightly lower temperature. That dense patch, held together by its own gravity a little more tightly, was a seed. Over billions of years, that seed would pull in more matter through gravity. eventually collapsing to form a galaxy cluster, a supercluster, the vast cosmic web we see. The cooler spots on COBE map were the future addresses of everything. The technological achievement was staggering. COBE instruments had to be exquisitely sensitive, operating from Earth orbit to avoid our atmosphere's interference. They confirmed two monumental things. First, the cosmic microwave background spectrum matched a perfect blackbody curve with astonishing accuracy, just as the Big Bang theory predicted for radiation from a hot, dense state. Second, and most thrillingly, it found the predicted anisotropies. This was the first direct evidence for the seeds of all cosmic structure. The angular scale of these fluctuations was broad, smeared over large patches of sky because COBE resolution was limited. It saw the biggest hills and valleys, but that was enough. It told us the blueprint was real. That map, a splatter of red and blue pixels on a screen, was our first glimpse of the infant universe's face. Not as a smooth mask, but as a landscape already rich with potential. It confirmed our origin story. It handed us the key to reading the cosmos's growth chart. The quiet hiss of the cosmos suddenly had a story to tell, and we had just learned to hear its first words. COBE gave us that first grainy photograph. It proved the ripples were real, but to really understand the story they were telling, we needed a sharper image. We needed a map so precise it could measure every hill, every valley in that ancient landscape. And that job went to two cosmic cartographers, the Wilkinson Microwave Anisotropy Probe at WMAP and later the Planck satellite. These weren't just telescopes. They were time machines tuned to the first whisper. Their mission was to measure the cosmic microwave background with a fidelity that could turn cosmology from speculation into a precise science. WMAP launched in 2001. It left Earth's orbit entirely, traveling to a special point in space, the second Lagrange point, 1,000,000 miles away. That distant, quiet vantage gave it a stable, unobstructed view of the whole cosmic sky, free from the interference of Earth's own warmth and radio noise. For 9 years, it scanned and re-scanned the heavens. Its instruments, far more sensitive than COBE, didn't just confirm the ripples, they measured their exact contours. The map it sent back was breathtaking. It looked like a cosmic egg mottled with shades of blue and red, a detailed tapestry of hot and cold spots. This wasn't just a picture anymore. It was a data set, a numerical blueprint of the infant universe. Planck, a European mission launched in 2009, took this even further. Its instruments were cooled to within a fraction of a degree above absolute zero. They became the most sensitive microwave detectors ever sent into space. The map Planck produced is to this day our definitive portrait of the primordial universe. It shows the temperature variations with a precision of a few millionths of a degree. But how do you read a map like that? How do you translate those splotches of color into the ingredients of reality? Scientists use a tool called the power spectrum. Think of the full sky map as a complex piece of music. The power spectrum is the sheet music. It breaks that music down into its individual notes. It plots the strength, the volume of the temperature fluctuations against their size, their angular scale on the sky. Do the fluctuations appear in large patches? Or in many small, sharp variations? The resulting graph doesn't look like random noise. It has a very specific shape, a series of distinct peaks and valleys. Like a cosmic barcode, and each peak in that barcode contains a universe of information. These peaks are the frozen echoes of sound waves. Remember the universe before recombination. That hot, dense plasma of particles and light. In that soup, gravity was constantly trying to pull matter together into clumps, but radiation pressure from the intense light was pushing it apart. This push and pull created oscillations. Bubbles of plasma would collapse under gravity, heat up, and then be blasted apart by radiation pressure, only to collapse again. These were literal sound waves ringing through the early cosmos. Then, at the moment of recombination, the music stopped, the universe became transparent, and those sound waves were frozen in place, imprinted as a specific pattern of slightly hotter and colder spots in the light. The first major peak in the power spectrum tells us about the geometry of the universe. Is space flat like a sheet of paper, or is it curved like a sphere or a saddle? The size of the largest fluctuations we see gives us the answer, and the data is clear. The universe appears to be flat, or so nearly flat we cannot measure the curvature. This has monumental implications. A flat geometry suggests the total density of matter and energy in the cosmos is exactly at a critical value, balancing the expansion perfectly. The second peak gives us the density of ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us. The third peak is the fingerprint of dark matter, that mysterious, invisible substance that interacts through gravity but not with light. By measuring the precise heights and positions of these peaks, scientists can extract the cosmic recipe with staggering accuracy. The Planck collaboration's final analysis gave us our modern cosmic inventory. The universe is about 5% ordinary matter, 27% dark matter, and a staggering 68% dark energy, the mysterious force driving the accelerated expansion of space. It also pinned down the universe's age with incredible precision. 13.8 billion years, we live in an era of precision cosmology. We have a standard model, a robust, mathematically sound description of the cosmos from its first fractions of a second to today. This is a triumph of human curiosity and engineering. Yet, for all its precision, this detailed blueprint has also revealed subtle cracks, tiny anomalies in the data that don't quite fit the perfect picture. A mysterious cold spot, a puzzling asymmetry in the fluctuations between one half of the sky and the other. These are not errors, they are whispers of something deeper. Perhaps a clue from the era before inflation, or a sign that our understanding of those first moments is still incomplete. The oldest light has given us answers of breathtaking clarity. And in doing so, it has posed new, even more profound questions. We have the map, the temperature map, the hills and valleys in that ancient light, but light carries something else. A direction, a preference in how it vibrates, that's polarization. And in that polarization, there could be a signature, a direct signature from the universe's first moment. A ghost from its explosive birth. Think of sunlight on a lake. The light scatters and it becomes polarized. Its waves vibrate in a particular direction relative to the water. Something similar happened. In the infant universe, just before that light was set free, photons were scattering off free electrons. That last scattering, it imprinted a pattern. It gave the light a faint orientation. So it's not a temperature map, it's a map of direction, a tapestry of tiny arrows across the sky. And scientists see two fundamental types in that pattern. The first are E-modes, like iron filings around a bar magnet, neat radial lines inward, outward. These come from the density fluctuations, the same clumps of matter, ordinary and dark, under gravity. We've mapped these E-modes, they confirm the story. The story the temperature map already told, but the second type, that's the frontier, B-modes. Imagine taking that pattern of iron filings and giving it a twist. The lines become swirled, a vortex. That kind of polarization can't come from simple clumps. It requires a twisting force, a shearing in spacetime itself. And there's one event powerful enough to do that, on a universal scale, the inflationary burst. The theory goes like this. In that first fraction of a second, space expanded exponentially. Filled with a storm of quantum energy that would have generated gravitational waves, ripples in the geometry of spacetime. As these primordial waves moved through the universe, they would have stretched and squeezed space in a rotating, twisting pattern. That motion would have imparted a swirl to the plasma, and when the light finally decoupled, that swirl was frozen into the polarization as a B-mode pattern. Finding that pattern would be like finding a fossil, the fossilized vibration of inflation's engine. Direct evidence that the inflationary epoch was real, and it would tell us about the energy, the incredible energy at which it happened. Andre Linde, one of inflation's architects, described it. Seeing the first tremors of creation, it could connect the cosmos to particle physics, to the most fundamental theories, maybe even offer a glimpse into grand unification. When all forces were one, the hunt for this signal is among the most difficult. The expected B-mode signal from inflation is incredibly faint, maybe 1/10,000,000th of the temperature signal. It's buried under a mountain of other effects. The biggest mimic is our own galaxy, interstellar dust. When it's aligned by magnetic fields, it can produce polarized light. Light that looks exactly like a B-mode pattern, so distinguishing the cosmic signal from the galactic foreground. That's the monumental challenge. This is where experiments like BICEP and the Keck array come in. At the South Pole, one of the driest, clearest places on Earth, these telescopes stare at a small, supposedly clean patch of sky. For years, they use sensitive detectors cooled to near absolute zero to measure the polarization with exquisite precision. The story of this search has been a roller coaster. A few years ago, one team announced a possible detection. A thrilling find, but later, with help from the Planck satellite's dust maps, they found their signal could largely be explained by galactic dust, a lesson in cosmic humility. The search continues with better technology, more careful analysis to tease out that primordial swirl from the foreground, from our own Milky Way. This pursuit is the cutting edge. It's no longer just about mapping the universe's infancy. It's about listening for the echo of its first cry. The hunt for primordial B-modes is a quest to touch the moment of Genesis, to find the imprint of the mechanism that set everything in motion. And if that imprint is there, hidden in the polarization of the oldest light, then it forces the next question. The deeper question: what could have triggered it? What existed before the inflation that began our reality? That cosmic barcode, the ancient light's power spectrum. It's a precise inventory, a way to weigh the universe without touching a single star. It's like a complex musical chord ringing from the dawn of time. Each harmonic peak in that chord reveals a different ingredient. The first peak tells us about the overall geometry, but the second and third peaks, that's where the real accounting happens. They're the fingerprints of the early universe's sound waves frozen in place, Baryon acoustic oscillations. To understand that, you go back to that hot, dense plasma before the first light escaped. Ordinary matter, protons and neutrons, baryons, was coupled tightly with light. Dark matter was already there, invisible, ghostly, only feeling gravity's pull. In that soup, gravity tried to pull a clump together, but the intense radiation pressure from the light pushed back. That created a pressure wave, a sound wave, literally rippling outward through the plasma. The baryons and photons were locked in this wave, with dark matter sitting quietly at the center, the gravitational anchor. Then, at recombination, the music stopped. The photons fled. The baryons, suddenly freed from the light's push, were left stranded at the edge of that sound wave. They formed a spherical shell around the original dark matter seed. The radius of that shell was set by how far sound could travel in those 380,000 years, about 500,000 light-years in the expanding universe of that time. That scale became a cosmic standard ruler imprinted on the distribution of matter. We see this ruler in two places. First, etched into the pattern of hot and cold spots in the cosmic microwave background itself. The characteristic size of the fluctuations gives us that measurement. Second, we see its echo billions of years later. Surveys mapping millions of galaxies find they're slightly more likely to be separated by a specific distance. That distance is the grown-up version of that same sound wave shell, stretched by the universe's expansion, a fossilized echo in the large-scale structure of the cosmos. Now back to the peaks. The relative heights of those peaks in the power spectrum are exquisitely sensitive to the amounts of baryons and dark matter. Here's why. The odd-numbered peaks, like the first and third, correspond to waves where the plasma was most compressed when the light was set free. If there are more baryons, more ordinary matter, they add extra mass to the plasma. That makes it harder for radiation pressure to push back against gravity. It enhances the compression, making the odd peaks taller. The even-numbered peaks, representing moments of rarefaction, are affected differently. Dark matter plays the crucial opposite role. It doesn't interact with light at all. It just sits there, providing gravitational pull. More dark matter means a stronger gravitational tug on the baryon photon fluid from the start. That suppresses the odd peaks relative to the even ones. It's a delicate balance. By measuring the precise heights and shapes of these peaks, especially with data from missions like Planck, scientists perform a cosmic forensic analysis. They fit a theoretical model with all its parameters for different densities to the observed data points. It's like matching a fingerprint. The suspect is the entire universe, and the pattern reveals its precise composition. The numbers from this analysis are definitive and humbling. Ordinary matter, the stuff of stars and planets and us, makes up only about 5% of the total cosmic budget. Dark matter, the invisible scaffolding holding galaxies together, accounts for about 27%. The remaining 68% is something even more mysterious, dark energy, which we infer from other measurements but whose signature is woven into this overall framework. This detailed accounting from the oldest light forces a profound confrontation. We've mapped the cosmos with breathtaking precision, yet 95% of it is made of substances we cannot see and do not fully understand. The light has given us the recipe, but we're still learning what the main ingredients truly are. We know dark matter is there, we can't see it, it doesn't glow, doesn't reflect light. But we can measure it. We measure it through the oldest light we have, the cosmic microwave background. That light acts like an X-ray. It shows the silhouette of dark matter through gravity. Think of the early universe as a shallow pool of water. You drop a pebble in, you get ripples. That's a tiny density fluctuation. Now imagine an invisible object, heavy, placed just under the surface where the pebble hit. You can't see the object, but the ripples change. They form faster, their shape is different. The water's surface shows you the hidden mass. That's what dark matter did. In the early plasma, ordinary matter, protons, electrons, was fighting with radiation. Light was pushing it apart, but dark matter was unaffected by light. It only felt gravity, so it got a head start. It could start clumping together from the very beginning, creating these invisible wells of gravity, anchors in a smooth cosmos. That head start is written into the cosmic microwave background, into the acoustic peaks. Those peaks are frozen sound waves from the plasma. Dark matter's early clustering changed the rhythm of those waves. Because it was already gathering into halos, it gave a stronger gravitational tug on the plasma from the start. That extra pull affected how the plasma sloshed. It suppressed the odd-numbered peaks, the compression phases relative to the even ones. The third peak is key. Its height, its position, that's a direct measure of dark matter's density. And the data shows it's lower than it would be if the universe was only ordinary matter. That suppression is the shadow, dark matter's shadow, cast on the ringing of the early cosmos. And the pattern tells us dark matter must be cold, cold meaning slow, moving slowly compared to the expansion. If it was hot, moving near light speed, it would have smoothed out the small fluctuations, washed away the seeds of galaxies. But the CMB shows fluctuations on all scales, even the very small. So the particles must be massive, slow-moving, letting those tiny seeds survive. From this data and others, we get a number. Dark matter outweighs everything we can see, stars, planets, gas, by about 5 to 1. It's the dominant matter. And this isn't from one clue, it's cross-verified. The density from the CMB matches other measurements. Look at galaxy rotation. Stars at the edge of spiral galaxies orbit too fast. The visible mass isn't enough to hold them. There has to be a dark matter halo. Look at gravitational lensing. A galaxy cluster bends light from behind it. The degree of bending shows the total mass, and it's always much more than the visible parts. So these lines of evidence, the ancient sound, spinning galaxies, bent light, they all converge. They give the same answer, a universe dominated by something invisible. The CMB did more than confirm it. It quantified it, constrained its nature, cemented its role in the standard model. But in solving that, it created a deeper mystery. We know what dark matter does. We don't know what it is. Is it exotic particles, something to be detected underground? Is it something stranger about gravity itself? The oldest light gave us the outline of the shadow. Now we have to find what casts it. The oldest light, though, it goes beyond just cataloging matter. There's a signature in it for something much bigger and stranger. Back in the late 90s, 2 separate groups of astronomers found something that broke a basic assumption. They were looking at distant supernovae, using them like mileposts to see how the expansion of the universe had changed over time. The expectation was that gravity, from all the matter out there, would be slowing that expansion down. The data said the opposite. The expansion wasn't slowing, it was getting faster. Some mysterious repulsive force, what we now call dark energy, was pushing space apart, accelerating the process. It was a huge discovery, Nobel Prize winning, but how could we be certain, and what did it have to do with that ancient light? The cosmic microwave background gives the independent, crucial proof that locks this strange picture in place. It comes down to geometry and distance, the pattern of hot and cold spots in the CMB, the specific angular size of those peaks, acts like a fixed ruler. We know its actual physical size from the physics of the early universe. It's how far a sound wave could travel before the light was freed. When we measure how big that ruler looks to us on the sky, we're measuring the geometry of all the space between us and that ancient surface. If the universe were positively curved like a sphere, the ruler would look bigger. If it were negatively curved like a saddle, it would look smaller. Data from WMAP and Planck is clear. The ruler appears exactly the size predicted for a flat universe. Space, on the largest scales, has no measurable curvature. A flat universe means something critical. It tells us the total density of all energy in the cosmos, matter, radiation, dark energy, has to be exactly at a certain critical value. The detailed fit of the CMB power spectrum gives us the matter density very precisely. But when we add up all the matter, ordinary and dark, it only comes to about 32% of that critical density. Something else has to make up the rest, 68%, to keep the universe flat. That something is dark energy. It's the missing piece the geometry requires. This is where it connects to the supernova. Knowing the universe is flat from the CMB gives us a precise cosmic yardstick. We can calculate the true distance to that CMB shell, the surface of last scattering. We can also measure its redshift, how much its light has been stretched. Comparing that distance and redshift with the distances and redshifts of the much more recent supernova reveals the expansion history. The supernova tell us the expansion is accelerating now. The CMB tells us that for the universe to be flat, dark energy must have been there, influencing the expansion for billions of years to produce exactly the distance we measure to that ancient light. The two pieces fit together. There's another, subtler clue in the ancient light itself, the integrated Sachs-Wolfe effect. As CMB photons travel for billions of years to reach us, they move through the evolving gravitational landscape of the growing cosmic web. If the universe's expansion were dominated by matter, these gravitational wells would stay constant. A photon falling in would gain energy, and climbing out would lose the same amount. No net change, but if dark energy is accelerating the expansion, it weakens these gravitational potentials over time. The wells become shallower as the photon passes through. The photon loses less energy climbing out than it gained falling in. That results in a very slight additional warming of the CMB in directions where it passed through large-scale structure. It's an incredibly faint signal, but statistical correlations between the CMB map and maps of millions of galaxies have detected it. It's a direct, late-time imprint of dark energy's influence on the journey of that first light. So the CMB is both a beginning and an end. It's the afterglow of the explosive birth, and it's the canvas where the fate of the cosmos is written. The precise size of its patterns tells us the universe is flat, which demands a dominant dark energy. Its detailed fluctuations, combined with other observations, sketch a history where this mysterious force now steers the expansion. The latest data from Planck pins the numbers down. Our universe is about 5% ordinary matter, 27% dark matter, and 68% dark energy, acting much like Einstein's cosmological constant, an energy inherent to space itself. This forces us to confront a universe whose ultimate destiny isn't a collapse or a coast, but an endless, accelerating drift into isolation. Galaxies beyond our local group will eventually be pushed away by expanding space faster than light can bridge the gap, fading from view for good. So the oldest light does more than show us our origins. It whispers about our future, a future written into the very geometry it helped us measure. This elegant model has a crack in it now. A persistent one. It's called the Hubble Tension. It's a disagreement between two of our best cosmic clocks, and it has people wondering if we've missed something fundamental. The problem is simple. How fast is the universe expanding right now? We have two precise ways to answer that. The first uses the cosmic microwave background. It's a distant anchor. By analyzing the pattern in that light, the Planck team could calculate the expansion rate. Their method looks backward. It starts with the infant universe 13.8 billion years ago. It runs the equations of our standard model forward to predict the rate today. That number came out to about 67.4 kilometers per second per megaparsec. It's a backward-looking prediction. The second method is local. It's direct. Astronomers like Adam Rees use the cosmic distance ladder. They measure distances to nearby stars with precision. They use those to calibrate distances to farther supernova. Those supernova act as standard candles. By seeing how fast those distant galaxies are moving away, they measure the expansion rate as it is now. Their value is consistently around 73, same units. The difference seems small, just a few percent, but in precision cosmology, it's huge. The gap is many times larger than the estimated errors for either method. It's like having two perfect Swiss watches, each checked and rechecked, and one reliably ticks faster than the other. The discrepancy isn't going away. With each refinement, with new data from telescopes like James Webb confirming the local measurements, the tension remains. So what does it mean? One possibility is a hidden error. Maybe our understanding of Cepheid variable stars has a flaw, or maybe there's an unaccounted effect in the Planck data analysis. Teams are scouring both methods. But if the tension is real, if it's not an error, then it points to new physics. Our standard model, lambda CDM, might be incomplete. The model assumes dark energy is constant. A cosmological constant. But what if dark energy isn't constant? What if its strength has changed over time? That could alter the expansion rate between the early universe and today. It could bridge the gap. Other ideas point to the early universe itself. Maybe something altered the physics before recombination, changing the size of that fundamental sound horizon we use as a ruler. Perhaps neutrinos have unexpected properties, or interact in ways we haven't considered. Some speculate about exotic dark matter, or early dark energy that briefly influenced the cosmos before fading away. The Hubble tension is a gift and a challenge. It reminds us the cosmic microwave background isn't a solved puzzle. It's an active data set. That ancient light gave us answers. Now it's posing one of the most pressing questions. It's pointing toward a potential revolution, a hint that our map of cosmic history might need a new, uncharted continent. That flat, elegant model has a crack in it, but there are other whispers in the data, faint signals. They seem to defy the foundations of our cosmic picture. The most famous one is called the axis of evil. It's not a malevolent force, it's a statistical alignment. When you map the largest scale fluctuations in the cosmic microwave background, the biggest hills and valleys across billions of light years, they don't appear random. They show a surprising alignment along a particular axis in the sky, and that's deeply puzzling. The cornerstone of modern cosmology is isotropy, the idea that the universe on the largest scales looks the same in every direction. There should be no special axis. The axis of evil suggests there might be one. It's like painting a random pattern on a sphere, then stepping back to see all the brushstrokes leaning the same way. This alignment is one of several anomalies. There's a hemispheric asymmetry. The average temperature in one half of the sky is very slightly different from the average in the opposite half. The universe might have a warmer side and a cooler side. Then there's the cold spot. In the southern hemisphere, a region much larger than expected is significantly colder than its surroundings. It's not just a blip, it's a vast, mysterious chill on the map of the infant cosmos. So, are these real features or just illusions? Scientists use statistical tools. They ask a simple question: how likely is it that a perfectly random, isotropic universe, one generated by our standard model, would, by pure chance, produce a map with features this unusual? They run millions of computer simulations, universes following the known rules, and they check how often a cold spot as extreme as ours appears, or an alignment as pronounced as the axis of evil. The answer is not very often. The probability is low, often quoted at around 1 in 1,000. That's not conclusive proof, but it's enough to raise eyebrows. To keep researchers digging, if these whispers are real, what could they be? The explanations go into exotic territory. The cold spot, for instance. One theory suggests it could be the imprint of a cosmic texture. A defect in the fabric of spacetime itself, a knot that formed during a phase transition in the early universe, leaving a faint gravitational shadow. Another, more speculative idea is that it could be a bruise, a collision scar from our universe brushing against another bubble universe in a vast multiverse. The alignment of the axis of evil could point to a pre-inflationary fingerprint, a remnant structure from the universe's birth that inflation stretched but didn't completely erase. Or it could hint that the shape of space is more complex than we think, that it has a non-trivial topology, perhaps even folding back on itself in a way that leaves a directional imprint on the largest scales we can observe. These anomalies are loose threads at the edge of our cosmic tapestry. They remind us that for all its precision, our standard model is just that, a model. A breathtakingly accurate one, but still a human construction, designed to fit the data we have. The axis of evil and its cousins are the data points that don't quite fit. They're the hints that our observable universe might be part of a larger, stranger reality. They push cosmologists to look beyond the elegant equations, to consider possibilities that sound like science fiction, a multiverse, a finite cosmos with a connected shape, an origin story even more ancient and complex than we've dared to imagine. The oldest light has given us a clear picture, but in its faintest, most subtle imperfections, it may be pointing toward truths we have only begun to glimpse. To understand where it all started, you have to look before the photograph. the cosmic microwave background shows us the universe at 380,000 years old. But that pattern, the hot and cold spots, that's a message from much earlier, from the first fractions of a second, a time so brief, so violent, it's hard to picture. That's the realm of cosmic inflation, a theory that solved puzzles like the horizon problem, and it made a prediction about the oldest light. It said the primordial seeds for everything should have a specific character. Their distribution should be nearly scale invariant. That's a technical term for a simple idea. It means the fluctuations stamped onto the cosmos had roughly the same strength, no matter their size. Whether you look at a patch that becomes a galaxy cluster or a supercluster, the initial gravitational kick was proportionally similar, and that scale invariance is what the detailed maps from Planck and WMAP confirmed. The pattern in the CMB lines up with the simplest models of inflation. It's like an echo of a single note struck at the dawn of time, resonating across all scales. Inflation says that in the first sliver of a second, space went through hyper-accelerated expansion, driven by a mysterious field often called the inflaton. And as this field evolved, its quantum fluctuations got stretched by the rapid expansion, from microscopic to astronomical sizes. These stretched fluctuations became the density variations, the slight over-densities and under-densities that gravity later amplified into galaxies. The CMB is our snapshot of those variations, frozen into the plasma. The near-perfect scale invariance we see is a clue. It suggests the energy of the inflaton field changed very slowly during the epoch that created our observable universe. It was like rolling down a very gentle, vast hill. Alan Guth, who first proposed the idea, and André Linde, who developed key variations, described this landscape. The shape of that hypothetical hill, what physicists call the inflationary potential, dictates everything. A steeper hill would produce different patterns in the CMB's fluctuations. It would create subtle correlations between hotspots of different sizes, features known as non-Gaussianities. Our current maps show the fluctuations are essentially Gaussian, random in a specific way, which again points to a simple, slow roll inflation. Future experiments will hunt for the faintest signs of these non-Gaussian correlations. Finding them would be like discovering the brushstroke style of the artist who painted the primordial canvas. But there's an even more sought-after signature, one that takes us to the most extreme physics. Gravitational waves generated during inflation would leave a distinct swirl in the polarization of the CMB, the B modes. The strength of this signal relative to the density fluctuations is called the tensor-to-scalar ratio, denoted by the letter R. This ratio is a direct window into the energy scale of inflation. A detection would tell us the incredible temperature of the universe during that explosive growth, likely 1 trillion times hotter than the core of our Sun. It quantifies the violence of the event. Measuring R is the holy grail for many cosmologists because it connects the cosmos directly to quantum gravity and grand unified theories. The challenge is monumental. It's the ultimate forensic exercise. We're trying to deduce the precise mechanics of a titanic explosion by only studying the settled dust patterns, the CMB, from an immense distance in time and space. Every detail in that dust pattern, every slight deviation from perfect randomness, is a clue to the engine of creation. This line of questioning leads to the precipice of the unknowable. What existed before our Big Bang? Inflation itself may have been a transitional phase from something else. Some theories, like eternal inflation or cyclic models, suggest our universe is one bubble in a vast multiverse or part of an endless cycle. The CMB might hold faint, indirect hints of such a larger reality. Anomalies like the cold spot, while not confirmed, keep such speculative doors open. So the cosmic microwave background is more than a baby picture. It's our primary link to physics at energies we can never recreate. It pushes our understanding to its limits, forcing us to contemplate not just how our universe began, but whether its beginning was truly the beginning, or just a new chapter in a story whose earlier pages we may never read. The most profound whispers in that ancient light might not be from our universe. They could be from a neighbor. That's the radical frontier now. The cosmic microwave background becomes a window, not just into our past, but into a vaster, hidden reality, a multiverse. The theory of eternal inflation says our universe isn't unique. It's a single bubble. It nucleated in an eternally inflating sea of spacetime. Other bubbles, other universes could be forming constantly, each with its own laws of physics, separated by expanding walls of false vacuum. And if two such bubbles formed too close together in that primordial foam, they could have collided. The energy released in that collision would have been titanic. A localized event at the dawn of everything. It would have left a mark, a distinct scar on the fabric of our newborn cosmos, imprinted onto the plasma just before it released the first light. That scar would still be there, frozen into the pattern of the CMB. It would appear not as a random hot or cold spot. It would have a specific geometry. A circular disk with an exceptionally sharp edge, a boundary where the temperature changes abruptly from the inside to the outside. This isn't the kind of feature you'd expect from random quantum fluctuations. It would be an anomaly with a signature shape, like finding a perfectly round water stain on a ceiling, suggesting a leak from a pipe in the apartment above. Theoretical physicists like Matthew Johnson and his collaborators have spent years modeling this, what such a collision would look like from inside one of the bubbles. They run supercomputer simulations to predict the precise temperature pattern it would carve into the cosmic microwave background. Then they take that predicted template, a specific kind of circular asymmetry, and search for it in the real data. From WMAP and Planck, it's a needle in a haystack search on the grandest scale, looking for one particular shape in a map of subtle splotches. Their work has turned up some intriguing candidates, but they are inconclusive. Regions in the CMB sky where the temperature pattern aligns, however faintly, with what a collision might produce. The famous cold spot is one area that's been scrutinized through this lens. Could its unusual size and temperature profile be the bruise from a long-ago encounter with another universe? The statistical evidence isn't strong enough to claim a discovery. The signal, if it exists, is buried deep in the noise, and the human brain is notoriously good at finding patterns, even where none exist. But the search itself transforms the meaning of the CMB. It's no longer just a relic of our own beginning. It becomes a potential message board, a surface upon which signals from beyond our cosmic horizon might have been posted. Think of it this way: we are confined to our bubble universe. We can never see what's outside its expanding walls. The light from other bubbles can never reach us. But if two bubbles touched in the first instance of existence, the shock wave from that contact propagated inside our bubble. It became part of our history before our first light was set free. So by studying the oldest light inside our universe, we might indirectly detect something from outside it. This line of inquiry is speculative, it's thrilling, and it exemplifies how cosmology pushes into philosophy. The CMB is our ultimate experimental data set for ideas that seem, at first glance, untestable. It grounds the dizzying concept of a multiverse in a concrete, observational quest. Even a null result helps. Failing to find any collision signatures constrains the theories. It tells us something about how likely such bubble collisions were in our particular cosmic neighborhood. So while we lack proof, the very possibility reshapes our perspective. That faint, cold glow covering the sky might be more than a self-portrait of our infant cosmos. It could be a palimpsest, with the faintest of ghost images suggesting a reality so vast our universe is but a single page. That plasma wasn't silent, it was ringing, a deep note vibrating through everything. For almost 400,000 years, the universe was this dense, searing fluid. Particles and light, and in that fluid, sound waves traveled. Not sound like we hear, but pressure waves, moving through a medium 1 billion times hotter than the sun's core. That was the music of creation, and then the universe became transparent, and the music just froze right in place. We hear its echo with telescopes. In the pattern of hot and cold spots in the cosmic microwave background, that phenomenon is called Baryon acoustic oscillations. Picture a crowded room. A really energetic room. The ordinary matter, protons and electrons, the baryons, they're like people packed in tight. The photons, the light particles, they're like this brilliant light filling the room, pushing everyone apart with radiation pressure, and gravity is this constant pull, trying to make the crowd huddle closer. In the early universe, baryons and photons were locked together. A single churning fluid. Now imagine a slight gathering of people in one spot. Gravity pulls more in, makes it denser, but as it compresses, the light's pressure builds up. Like heat in a cramped space, that pressure gets too strong and it pushes the crowd back out. They overshoot. They create a region that's now less dense than average. Then gravity pulls again. This push and pull created oscillations, standing waves of density, sloshing back and forth through the cosmic fluid. They were literal sound waves. The radiation pressure was the restoring force. The key is the timing. These oscillations had a specific rhythm, a frequency set by the physics of the plasma. They could only complete a certain number of cycles before the music suddenly stopped. That stop was recombination, when atoms formed and the photons decoupled. The pressure vanished, the waves froze instantly. Whatever state a region of plasma was in at that exact moment, whether it was at peak compression, or the trough of rarefaction, or somewhere in between, that became permanent. That state determined whether that patch of sky would be slightly hotter or colder in the cosmic microwave background. Think of it like a pond. On a perfectly still day, the moment it completely freezes solid. If you'd been dropping stones into the pond at regular intervals before the freeze, the overlapping ripples would create a pattern on the ice. The size of the circular waves tells you how fast the ripples moved. The pattern of peaks and troughs tells you the timing of the drops. Our universe did exactly this. The stones were the primordial quantum fluctuations. The water was the photon baryon fluid, and the moment of recombination was the great freeze. The pattern left on the cosmic ice is the CMB map. Scientists translate that map into a graph. The power spectrum, it plots the strength of the temperature fluctuations against their angular size on the sky. This graph doesn't look random. It has a series of distinct peaks and valleys. Like a cosmic barcode, the first major peak corresponds to regions of the plasma that had just reached their first maximum compression when the universe became transparent. They were at their hottest, most dense state. The second peak corresponds to regions that had just rarefied, reaching their maximum expansion, their coolest state. The third peak is the next compression, and so on. The precise height and spacing of these peaks are a forensic record. They tell us the density of ordinary matter. Because more baryons mean a heavier fluid that oscillates differently. They tell us the density of dark matter, which provides a gravitational anchor but doesn't participate in the sloshing. They even confirm the geometry of space. Most importantly, these oscillations created a standard ruler. The sound waves could only travel so far in the time before recombination. That maximum travel distance, the sound horizon, got frozen into the fabric of the cosmos. In today's expanded universe, that scale is about 500 million light-years. We see its imprint in two places. First, directly in the CMB, as the characteristic size of the hot and cold spots. Second, and astonishingly, we see its echo billions of years later in the distribution of galaxies. Modern galaxy surveys show that galaxies are slightly more likely to be separated by this specific scale, a fossilized bubble from the early universe's sound. It's a consistent measuring stick across cosmic time, and it confirms our model with breathtaking consistency. The oldest light carries a melody, and by learning to read its notes, we've deciphered the composition of the cosmos itself. That frozen sound gives you a temperature map, but light carries more than heat. It carries direction. Every photon from the cosmic dawn vibrates in a specific way as it travels. That property is called polarization. It's a hidden layer of information, a subtler message written into the orientation of those ancient waves. To understand it, you go back to that final moment of scattering. Just before the universe became transparent, a photon had its last collision with a free electron. The way it scattered, the direction it bounced, depended on the pattern of light hitting that electron from all sides. If the radiation field was perfectly uniform, the scattering would produce no net polarization. But if there was an anisotropy, a difference in temperature or intensity from different directions, that last scatter would imprint a preferred vibration direction onto the escaping photon. The polarization direction ends up perpendicular to the temperature gradient on the sky. So imagine a slightly warmer spot next to a slightly cooler one on that primordial surface. The electrons at the boundary experience a push from the hotter, more intense side. The photons that scatter away carry a polarization pattern that points, like a tiny arrow, along the contour lines between hot and cold. This creates a distinctive, web-like pattern across the entire cosmic background. Scientists call these E-modes. They look like the field lines around a magnet, radiating inward or outward from points. These E-modes are generated by the same scalar density fluctuations, the same hills and valleys of matter that created the temperature map. They are a confirmation. A consistency check written in light's geometry. They tell us about the velocity of the electron fluid at the exact moment of last scatter, whether the electrons were moving toward an overdensity or away from it. This polarization is the universe's own magnetic strip, encoding the dynamics of that final instant. But there is another, more elusive pattern, B-modes. These have a swirled, curling geometry, like the pattern left in water after stirring it. They cannot be created by simple density clumps. Generating a curl requires a twisting force. In the context of the cosmic microwave background, there are two potential sources. The first is gravitational lensing. As the CMB light travels for billions of years, the gravitational pull of all the intervening dark matter and galaxies subtly warps its path. This weak lensing can twist some of the E-mode polarization, converting a small portion into B-modes. This is a late-time effect, a signature of the cosmic web's growth. The second potential source is far more profound. Primordial gravitational waves, ripples in the fabric of spacetime itself, generated during the violent epoch of cosmic inflation. These waves would have stretched and squeezed space as they passed through the primordial plasma, imparting a genuine primordial curl to the motions of matter and radiation. That curl would be frozen into the polarization as a primary B-mode signal. Finding this primordial B-mode signal is the next great frontier. It is a direct probe of inflation at energy scales 1 trillion times beyond what any particle collider can reach. Experiments like the Simons Observatory, with its array of ultra-sensitive telescopes in Chile's high desert, and the Future CMB S4 project, are designed specifically for this hunt. They use detectors cooled to a fraction of a degree above absolute zero to measure the faint polarization with unprecedented precision. Beyond testing inflation, this richer polarization dataset helps break degeneracies in our cosmic models. For instance, the lensing-induced B-modes provide a map of the distribution of all matter, dark and light, across cosmic history. This allows independent measurements of the mass of neutrinos, those ghostly particles that stream freely through the universe. By seeing how they suppress the growth of the smallest structures, cosmologists can weigh the neutrino, constraining physics at both the largest and smallest scales. So the polarization is not just an add-on, it is a deeper, more nuanced language, where the temperature map tells us the what, the structure of the infant cosmos. The polarization begins to tell us the how things were moving. What forces were twisting the fabric of reality in its first fleeting moments. It pushes our observational technology to its absolute limits, all to read a message written in the faintest whisper of oriented light. A whisper that has crossed the entirety of time to reach us. Those photons from the beginning, they didn't just move through empty space. Their trip, 13.8 billion years, it wasn't a straight line. It was a winding path, because the universe kept evolving, a gravitational landscape forming. Every galaxy cluster, every dark matter filament, every big structure that grew after the cosmic dawn, each one exerted a tiny pull, bending the light's path like a glass lens bends light. That's gravitational lensing, but applied to the oldest picture we have. For a long time, cosmologists saw this lensing of the cosmic microwave background as a nuisance. A blur. It smeared the fine details of that primordial pattern, made precise measurements harder. But then they realized something. That blur wasn't noise. It was a signal that painted a map of everything that came after. Think of it like a perfect, pristine photograph from the distant past. Then, over billions of years, that photograph gets covered by a sheet of bumpy, warped glass. The glass is the whole cosmic web of matter that grew in between. When we look now, we see a slightly distorted image. The bumps in the glass have stretched and squeezed the picture subtly. But by analyzing those distortions, how the original patterns got remapped, we can actually reconstruct the shape of the glass. We can map the bumps, and since those bumps are mass, visible and dark, we're making a mass map of the universe. The cosmic microwave background becomes the ultimate backlight, and everything in front of it casts a gravitational shadow. The process is statistical detective work. Scientists don't see a single photon bend. They look at the correlations it creates. The lensing effect mixes up different Fourier modes, the mathematical building blocks of the CMB's temperature and polarization maps. It introduces specific, predictable correlations between modes that should be independent. By measuring these correlations across the whole sky, algorithms can work backward. They estimate what's called the lensing potential, a mathematical field that describes how much and in which direction every point on that primordial sky was shifted by all the intervening matter. From this potential map, they reconstruct a two-dimensional projection, a map of the total mass integrated along the entire line of sight from us to the surface of last scattering. A simple analogy, looking at a printed page through the curved bottom of a wine glass. The text appears distorted, stretched, and compressed. You can't see the glass itself. But by studying the precise pattern of distortion in the letters you can deduce the shape, the thickness, the curvature of the glass. The CMB's acoustic peaks, those regular, predictable sound wave fossils, are our known text. The gravitational lensing from the cosmic web is the wine glass. By seeing how those peaks are smeared and remapped at very small angular scales, we infer the distribution of the matter that did the lensing. This lensing leaves a clear signature. It smooths out the sharp higher acoustic peaks in the power spectrum, and crucially, it generates a specific polarization pattern. Remember the E-modes, the radial patterns from density variations. Gravitational lensing can twist some of those E-modes, converting a portion into the swirled B-mode pattern. These are lensing B-modes, a secondary effect distinct from any primordial B-modes from inflation, but no less valuable. Their strength directly traces the total amount of matter along the line of sight. The Planck satellite's measurements of this were a milestone. The collaboration produced a full sky map of the lensing potential. It's a fuzzy but definitive map of the projected cosmic mass distribution. This map aligns with what we expect from our standard model of structure formation. It provides an independent, clean probe of dark matter because lensing responds to all mass, visible or not. It also tracks the growth of structure over time. Combining this lensing map with other probes like galaxy surveys gives a consistent story of how gravity pulled matter into the web we see. So the oldest light has a dual purpose. It's a snapshot of the infant universe, but it's also a flashlight we shine through the cosmos. The shadows and distortions it picked up on its journey reveal the hidden architecture of everything that grew after. It connects the smooth beginnings to the clumpy present, a single, coherent narrative written in light and gravity. That map of gravitational lensing shows the cosmic web of matter. But then there are the pieces that hardly interact with anything. The universe is full of ghosts, trillions of them passing through you right now, and they have been since the cosmos was less than a second old. These are cosmic neutrinos, and the ancient light holds their faint signature too. Neutrinos are the most elusive particles we know. They have almost no mass, no electric charge. They interact with ordinary matter so rarely they could fly through a light year of solid lead without a single collision. In the first second after the Big Bang, the universe was so hot and dense that even these ghostly particles were trapped, colliding constantly in the plasma. But as space expanded and cooled, they broke free. They decoupled from the cosmic soup, and from that moment on, they've been streaming freely across the universe. A relic sea from its fiery infancy, this early decoupling, this free streaming, left a specific fingerprint on the cosmic microwave background. To see it, you think about structure formation. Those slight over-densities in the early universe, the seeds for future galaxies, they grew by pulling matter in through gravity. But neutrinos, once free, don't clump easily. They move at nearly the speed of light, so they stream out of any gravitational well almost as quickly as it forms. This free streaming acts like a cosmic pressure. It smooths out the tiniest density fluctuations. It suppresses the growth of structure on the smallest scales, and that suppression is imprinted on the CMB's acoustic peaks. The effect is subtle but measurable. It primarily alters the relative heights of the peaks, especially around the third peak and at higher multipoles, the finer details of the power spectrum. The presence of free-streaming neutrinos makes these small-scale fluctuations slightly less pronounced than they would be otherwise. It's as if the ringing of the primordial plasma had a faint damper applied to its highest notes. A damping caused by particles that refuse to be tied down. Cosmologists measure this with two key parameters. The first is the effective number of neutrino species, called NFF. The standard model of particle physics, with its three known types electron, muon, and tau neutrinos, predicts this number should be about 3.046. The precise data from the Planck satellite aligns with that prediction. The CMB tells us the count of light relativistic species from the early universe matches what our particle colliders tell us. It's a consistency check across the vastest and smallest scales. The second, even more profound parameter is the sum of neutrino masses. For decades, neutrinos were thought to be massless. We now know they have a tiny mass, but pinning down exactly how much is incredibly difficult in a lab. The cosmos provides the scale. Free-streaming neutrinos with more mass would have slowed down earlier in cosmic history, transitioning from relativistic speedsters to slower-moving particles. This would change how efficiently they suppress small-scale structure. Heavier neutrinos would suppress growth more effectively, leaving a clearer mark on the distribution of galaxies and on the CMB's lensing potential. Planck data, combined with measurements from large-scale galaxy surveys, places a tight upper limit on this total mass. The current constraint says the sum of the masses of all three neutrino types is less than about 0.12 electron volts. To grasp how small that is, a single electron has a mass of over 500,000 electron volts. These are the lightest massive particles we know of. This cosmological measurement is now a driving input for particle physics. It tells experimentalists what range to look in. It helps distinguish between different possible hierarchies of neutrino masses. And perhaps most excitingly, if the true sum is found to be significantly above zero, it could point to other, even more exotic light particles from the dawn of time. So the cosmic microwave background does more than map matter and dark energy. It acts as a delicate scale, weighing the lightest things in existence. It uses the entire history of cosmic structure as its laboratory. Those ghostly neutrinos, born in the first second, have been whispering their secrets into the fabric of the cosmos for billions of years. And by reading the oldest light with exquisite care, we have finally learned to listen. The universe isn't just a collection of things, it's a space that has a shape. And the question is whether it's finite or infinite, whether it curves back on itself or just goes on forever. For a long time, those were philosophical questions. Now they're questions of measurement, and the answer is written in the sky, in the pattern of hot and cold spots we see in the oldest light. That light is the cosmic microwave background. And it acts like a protractor for the whole cosmos, because there's a standard ruler frozen into it, the sound horizon from the early oscillations. We know its physical size. How big it looks to us, its angular size on our sky, that depends entirely on the geometry of the space between it and us. It's a piece of trigonometry. If the universe had positive curvature, like a sphere, parallel light rays would converge. That same physical ruler would look bigger to us. It would span more than a degree on the sky. If the universe had negative curvature, like a saddle, the rays would diverge. The ruler would look smaller, and in a flat universe, a Euclidean universe, the ruler would appear at its true scale. About 1 degree across, and that's exactly what we see. The first peak in the CMB power spectrum sits right at the multipole moment for 1 degree. The data from WMAP and Planck are clear. The universe is spatially flat to a precision of about 0.4%, so that's a cornerstone. It tells us the geometry we learned in school, that the angles of a triangle add to 180 degrees. That holds for the cosmos itself. But this flatness has a direct implication. There's a specific critical density required to make space flat, and the measured flatness means the actual average density of the universe is exactly at that critical value. It's a perfect balance. For billions of years, that balance was between the energy of expansion and the gravitational pull of all the matter. A flat universe is poised between two fates: eternal expansion and eventual collapse. It's a universe that should have been finely tuned from the start, and that's one of the key puzzles that cosmic inflation was meant to solve. Inflation's explosive stretch would have flattened any initial curvature. Like blowing up a balloon until any small patch looks flat. So the CMB's verdict of flatness confirms that picture, but this answer deepens a mystery. Because we've measured the ingredients, ordinary matter and dark matter together make up only about 32% of the critical density needed for flatness. The other 68% is dark energy. That's what's required to make the books balance. So the universe is flat not because of matter, but because of this dominant component we don't understand. The geometry gives us the total, but the breakdown of that total shows our ignorance. We live in a cosmos that's flat, finite in age, but likely infinite in extent. Its geometry shaped by a force that now governs its fate. The oldest light measured the angles of the largest possible triangle and found them to be exactly what you'd draw on a flat sheet of paper. In that measurement is a universe of consequence. That flat geometry, those frozen sound waves, they give us the starting conditions, the first frame of a movie that runs for 13.8 billion years. We have the opening snapshot, the cosmic microwave background, and we have the laws of physics, the script for how gravity and matter interact. You put them together and you can press play. You can simulate the whole history of cosmic structure, from subatomic jitters to the grand tapestry of galaxies. That's the power of modern cosmology. It's not just looking back, it's taking that first frame and running the simulation forward to see if it matches the universe we live in now. The seeds are all there in the CMB. Those tiny temperature anisotropies, those 1 part in 100,000 variations, their statistical properties are exactly what you'd need. They're Gaussian, following a specific, random bell curve distribution. They're adiabatic, meaning the fluctuations in matter and radiation were in sync. And they have that nearly scale invariant power spectrum, the signature of inflation. These aren't just abstract measurements, they are the initial density field. The slightly denser patches revealed by the cooler spots on the map are the future addresses of everything. They're where gravity gets a head start. With these initial conditions coded into a supercomputer, cosmologists can model the Dark Ages, the period after recombination when the universe was a neutral, expanding fog of hydrogen and helium, lit only by the fading afterglow. In the simulation, nothing happens visibly for millions of years, but invisibly, gravity is at work. The dark matter, which began clumping even before the first light escaped, forms an invisible scaffolding. Its gravitational wells deepen, slowly pulling the ordinary baryonic gas into its embrace. The overdensities from the CMB map begin to grow. They amplify through gravitational instability. A region just 1% denser than its surroundings will attract more matter, becoming 2% denser, then 4%, in a snowball effect over cosmic time. The simulation runs, the first nonlinear structures collapse, dark matter halos merge and grow. Within the densest knots of this cosmic web, pockets of gas become so dense and hot that nuclear fusion ignites. The first stars blaze to life, ending the Dark Ages. Their fierce ultraviolet radiation begins to tear electrons from neutral hydrogen atoms, reheating and reionizing the universe in a process that took hundreds of millions of years. This epoch of reionization leaves its own faint imprint on the CMB's polarization, another clue that aligns with the story. Galaxies form, tracing the dark matter web. They cluster in groups and vast filaments, with immense voids between them. The simulation produces a predicted large-scale structure for the universe today. And here is the test. We can compare that prediction to reality. Massive galaxy surveys like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies. They measure the galaxy correlation function, how likely two galaxies are to be found at a given separation. The observed clustering pattern matches the prediction from the CMB initial conditions with stunning accuracy. It confirms the gravitational growth story. It validates that the same seeds that made the CMB hot and cold spots grew, under the influence of dark matter and dark energy, into the cosmic web we observe. This turns cosmology into a genuine predictive science. We don't just observe the past and the present separately. We have a causal chain. The CMB gives us the initial state. Our physical laws provide the dynamics, and the present-day galaxy distribution is the outcome. The fact that these three pieces fit together so precisely is the strongest evidence we have for our entire cosmic narrative, the lambda-CDM model. It means the ancient light is more than a relic. It is the foundational data point for a cosmic growth chart, allowing us to trace the path of everything, from a nearly smooth beginning to the structured, luminous universe we call home. The dark ages of the universe didn't last. A new chapter started, written in fire. Hundreds of millions of years after that first light was set free, something happened in the gloom. The first stars ignited. They weren't like stars today. They were monsters, behemoths of hydrogen and helium, they burned ferociously and died young in supernova. Their light was different, not the gentle glow of the cosmic background. It was a searing ultraviolet radiation, and this new light began to tear the universe apart. Atom by atom, this process is called reionization. Remember the neutral hydrogen from recombination, those simple atoms. The ultraviolet photons from the first stars and early galaxies were so energetic they could blast electrons right off. They ripped the universe apart, turning the neutral fog back into a plasma, free electrons and protons. It was like reheating a frozen soup. The cosmos became ionized again. More diffuse and patchy than before, this late event left its own signature on the oldest light. As the CMB photons, already on their journey, passed through this reionized gas, about 10% of them had one last encounter. They scattered off the newly freed electrons. This wasn't the last scattering at 380,000 years. This was a secondary scattering. A faint echo hundreds of millions of years later, and that echo is detectable. It's written in the polarization. That last-minute scatter imprinted a new pattern on the light. On the very largest scales of the sky, it shows up as an enhancement in the E-mode polarization power spectrum at the lowest multipoles, the biggest patterns we can measure. Think of it like finding a later signature in the corner of an ancient parchment. The original text is the CMB from recombination. The new signature is the scroll from reionization. Cosmologists measure this with a parameter called tau, the optical depth to reionization. It tells us how much the CMB light was blurred by this late scattering. By fitting the observed polarization pattern on those large scales, missions like WMAP and Planck pinned down a value for tau. This number isn't abstract. It translates into a timeline. It tells us when, on average, the first luminous structures lit up and began reshaping their environment. The data suggests reionization was rapid. Not a slow, gradual brightening, it was a dramatic transformation, likely centered around a redshift of 8, about 600 million years after the Big Bang. This is the epoch when the first galaxies and stars assembled in sufficient numbers to flood the cosmos with ultraviolet radiation, enough to tear apart the neutral hydrogen fog. So the cosmic microwave background shows more than the newborn universe. It also carries the shadow of its adolescence. That faint polarization signal is the imprint of the first dawn. It marks the moment the Dark Ages ended and the era of light truly began. Stars, galaxies, eventually us. We're using the oldest photograph to see the flash of the first fireworks that illuminated the cosmic night. The faintest whispers in that ancient light, we haven't fully heard them yet. Our current maps are masterpieces, but they're not the final word. A new generation of eyes is turning toward the cosmic dawn. Instruments so sensitive they'll listen for the heartbeat of inflation itself. Projects like the Simons Observatory in Chile's Atacama Desert and the monumental CMB S4 planned for both Chile and the South Pole. That's a quantum leap. These aren't single telescopes. They're vast arrays of thousands of detectors operating in some of the driest, coldest, most stable environments on Earth. Their goal is to move us from precision cosmology into discovery cosmology, where each new measurement could reveal something fundamentally unknown. Their primary target is the holy grail we discussed earlier, the primordial B-mode polarization. The swirl imprinted by gravitational waves from cosmic inflation. Current experiments have pushed the limits, but the next generation aims for a sensitivity that can detect a tensor to scalar ratio, R, smaller than 0.001. To grasp that challenge, it's like trying to measure the warmth of a single candle on the moon using a telescope on Earth while filtering out the glare of our entire galaxy. If that signal is there, these observatories will find it. A detection would be a direct line back to the universe's first trillionth of a second. confirming inflation and revealing the phenomenal energy scale at which it occurred. A null result, though, that would be equally revolutionary, ruling out whole classes of inflationary models, forcing theorists back to the drawing board. But the ambition extends far beyond B modes. These observatories will examine the very color of the cosmic microwave background with microscopic precision. The CMB spectrum is a near-perfect blackbody, but subtle distortions, deviations from that perfect curve are predicted. These spectral distortions are like forensic stains on the ancient light. Evidence of energy being dumped into the cosmic plasma at different epochs. One type, called a Y distortion, could be caused by the hot gas of galaxy clusters scattering the CMB photons. That's a known effect, but another, a micro-distortion, is a relic from much earlier. It could be a signature of energy release from the first stars, from decaying dark matter particles, or even from the evaporation of primordial black holes formed in the universe's first second. Measuring these distortions is like taking the cosmic background's temperature with a thermometer 1,000,000 times more accurate. Searching for the faint fever of long-forgotten cosmic events, and then, by mapping the Sonifying-Zeldovich effect, the slight boosting of CMB photon energy as they pass through the hot gas of galaxy clusters across the entire sky, these next-generation surveys will effectively conduct a cosmic census. They'll find every massive galaxy cluster in the observable universe, tens of thousands of them, regardless of how faint their light. This universal cluster catalog becomes a powerful scale for measuring the growth of structure over time. An independent and stringent test of dark energy models and the sum of neutrino masses. This monumental effort is driven by breathtaking technological innovation. The detectors at the heart of these projects are superconducting bolometers, cooled to a fraction of a degree above absolute zero. They're so sensitive they can detect the minute heating caused by a single microwave photon. Managing and analyzing the torrent of data they produce requires cutting-edge machine learning algorithms and supercomputing, turning raw signals into maps of the sky. It's a deeply interdisciplinary endeavor, uniting cosmologists, particle physicists, and engineers. We're on the verge of upgrading our view of the microwave sky from a standard telescope to the equivalent of the Hubble Space Telescope. The ancient light has already told us so much about our origins and composition. It continues to be our most valuable cosmic archive. Its next chapters of revelation are just beginning. With these new tools, we're poised to either solidify the foundations of our standard model of cosmology, or, perhaps more thrillingly, to uncover the cracks that lead to the next great revolution in our understanding of the universe. This knowledge changes how we see everything. For thousands of years, we thought of the universe as this static thing, maybe eternal, centered on us. But the cosmic microwave background tells a different story. It's the proof that our universe had a beginning, a specific, fiery start from a hot, dense state where everything came from. That fact has a huge philosophical weight. It means we're not in some eternal, unchanging arena. We're inside a narrative, a story with a first chapter, and we've read it, that we can read it at all, that the universe follows consistent laws we can write in mathematics. That's a profound truth. It suggests a cosmos that's knowable in principle. Eugene Wigner talked about the unreasonable effectiveness of math in science. The CMB is a stunning example. Equations we wrote on Earth predicted a specific pattern of frozen sound waves in the sky, and our telescopes found it with astonishing precision. This comprehensibility is a gift. It means we're not just passive inhabitants of a mystery. We're participants in a grand act of discovery. This journey reshapes our sense of place. The Copernican principle, the idea we don't occupy a special central spot, has been tested on the largest scales. The cosmic microwave background is isotropic. It looks essentially the same in every direction. There's no center to the expansion we can see, no up or down in the cosmos. We're on a rocky planet orbiting an ordinary star in the suburbs of a typical galaxy, adrift in a vast, homogeneous universe. That's a humbling demotion from the cosmic center. But in another sense, it's a promotion of breathtaking scope, because we are the part of the universe that has become conscious and can look back. Carl Sagan said we are a way for the cosmos to know itself. The atoms in our hands, our eyes, our brains were forged in ancient stars and scattered when those stars died. We are not just in the universe is in us. And with science, it has begun to understand its own origins. This leads to one of the most haunting questions from the data: the fine-tuning of the initial conditions. For the universe to make galaxies, stars, planets, and life, the numbers had to be just right. The density of the primordial fluctuations, the balance between matter and radiation, the strength of the fundamental forces. If any of these were slightly different, even by a fraction of a percent, the cosmos would be a barren void or a collapsed mess. The flat geometry we measure, which needs a precise balance of energy, is part of this puzzle. Why does the universe appear so exquisitely tuned? Some see this as evidence for a deeper principle, maybe a multiverse where every possible set of constants exists somewhere. Others see it as a remarkable fact for future physics to explain. For now, it's a silent question written into the oldest light, reminding us of our incredible, fragile good fortune to be here at all. The scale of time is maybe the most dizzying revelation. The universe is 13.8 billion years old. Human civilization spans a few thousand years. Our entire recorded history is less than a blink in cosmic time. One way to grasp this is a thought experiment. Compress the entire history of the universe into a single calendar year. The Big Bang happens at the first instant of January 1st. Our solar system forms in early September. The first multicellular life appears in mid-December. Dinosaurs roam in the final week of December and go extinct on the morning of the 30th. All of human history, from the first cities to now, unfolds in the last minute before midnight on December 31st. And yet, within that final second, we've built instruments that can perceive the first few minutes of January 1st. We can see the afterglow of creation's dawn. This contrast isn't meant to diminish our existence, but to elevate our curiosity. In a universe so ancient and vast, our fleeting moment of awareness is the spark that illuminates the whole. It gives us a unique responsibility, the responsibility to learn, to steward our tiny, precious world, and to continue the story of exploration. The cosmic microwave background is more than data. It's a mirror. In its faint, cold glow, we see our own profound journey reflected. From stardust to storytellers grasping for meaning in the magnificent dark. The story gets tangled sometimes. People hear about the cosmic microwave background and the Big Bang, and the real meaning gets lost, so there are a few things that get mixed up. The Big Bang wasn't an explosion, not like a bomb going off in some empty space. That's the picture, but it's wrong. What it was space itself expanding. From a state that was incredibly hot and dense, there wasn't an outside for it to explode into. Space and time, all of it, was part of that starting condition. A better way to think of it is a balloon inflating. The galaxies on the surface, they aren't moving away from a center on that surface. The space between them is just stretching. The expansion happened everywhere at once. It's still happening everywhere, and that connects to the second thing. The cosmic microwave background. We say the light comes from 13.8 billion light years away. Which is true in terms of how long the light has traveled, but that makes you picture a shell, a distant bubble with us at the center. That's not right. The CMB comes from everywhere. It was emitted when the whole universe became transparent, all at once, from every single point. The light we see from one direction started its journey from a place that's now incredibly far away. The light from the opposite direction started from a place just as far in the other direction. We aren't at the center. any observer anywhere would see themselves surrounded by this background light coming from their own horizon. It's a universal thing, not a distant object, and it's often called the afterglow of the Big Bang, which is close but not exactly. The Big Bang is that initial hot state, the start of expansion. The CMB is the afterglow of a later event, the era of recombination, when the universe cooled enough for atoms to form and light to finally travel freely. That was about 380,000 years after the initial moment, so the CMB isn't a snapshot of the Big Bang, it's more like a baby picture. The universe as a toddler taking its first steps, then there's the smoothness. The temperature of the CMB is almost perfectly uniform, and that can make it seem like the universe is boring. The same everywhere, but that confuses the scale. That isotropy, that sameness in all directions, it's a property of the largest scales we can see. It doesn't mean there's no complexity. It's like looking at a coastline from an airplane. From way up, it's a smooth, simple line. But when you're on the beach, you see every grain of sand, every rock. The large-scale smoothness was the canvas. The tiny imperfections in it, those were the seeds that gravity grew into galaxies, stars, planets. Into us, the uniformity tells us about the starting conditions, not the final, detailed picture. There's an analogy for this. The expanding universe is like a loaf of raisin bread dough rising. The raisins are galaxies. As the dough rises, the space between every raisin expands. No raisin is the center, and the oven's heat. Even after you take the loaf out, the warmth is still inside it, in every part. That lingering warmth is like the cosmic microwave background. It's not coming from the crust or the edges. It's the residual heat from when the whole loaf was baking. Now cooled and faint, but still there, detectable from within any slice. Correcting these ideas, it's not about being picky. It's about what the evidence actually says. The real story: space stretching, a universal transparency event, a smooth beginning that leads to a structured now. It's more elegant, more awe-inspiring. It grounds the story not in metaphor, but in that faint, cold light that fills the entire sky, a light that every point in the cosmos can call its own. The oldest light might hold more than just the story of the cosmos. It could hold a message. That's one of the most speculative ideas out there, that the cosmic microwave background could actually intersect with the search for intelligence. The CMB is the most universal signal we know. It fills every part of space. It's the ultimate background. So if you were an advanced civilization trying to communicate across stars or even between galaxies, what better reference frame could you have? Its properties are predictable. They're isotropic. Any species that develops cosmology would know them. Some have suggested such a civilization might use the CMB as a natural lighthouse. A timing signal, the consistent frequency of its blackbody peak or the specific pattern of its acoustic peaks could serve as a cosmic clock, a universal coordinate grid. If you wanted to send a signal that could be understood anywhere, you might encode it as a deviation from this expected background. You'd modulate your message against the steady hum of creation itself. That moves into even more speculative territory, the concept of cosmic engineering. A civilization that reaches a Kardashev Type 3 scale, harnessing the energy of a whole galaxy, would produce waste heat on a staggering level. That waste heat, if not perfectly managed, would have a thermodynamic signature, and some have wondered if that signature could be imprinted on the cosmic microwave background. Maybe as a subtle distortion in its perfect blackbody spectrum, or as an anomalous pattern in its large-scale anisotropies. Could a vast array of energy-harvesting structures like Dyson spheres create a collective infrared glow that blends into our measurements of the primordial light? It's a thought experiment. It pushes the limits of imagination. It asks if the canvas of the early universe could one day bear the brushstrokes of intelligence. There are more grounded ideas within SETI. The predictable nature of the CMB makes it an excellent calibration tool. An advanced civilization might use it as a backdrop for their own interstellar radar, or as a standard to correct for universal expansion when aiming communications. For us, as listeners, the CMB provides a quiet, uniform noise floor. An artificial signal, especially a powerful, narrow-band one, would stand out starkly against it. In that way, the ancient light creates the silent room where we might one day hear a whisper. This speculation reached a curious peak with what some called the Big Bang bounce hypothesis. A few researchers looked at certain large-scale anomalies in the WMAP data, the cold spot, the hemispheric asymmetry. They playfully suggested these could be of artificial origin, a signature of a pre-inflationary universe, or even a message. The scientific consensus, of course, overwhelmingly favors natural astrophysical origins. These features are far more likely to be clues about quantum gravity or cosmic textures than alien engineering. But the exercise is valuable. It stretches our perspective. It forces us to ask what the ultimate limits of observation might be. If intelligence can become a cosmic force over billions of years, could its artifacts blend into the very fabric of the universe? Could they become indistinguishable from natural phenomena? While these ideas reside firmly at the fringe of science, they serve a purpose. They connect two of humanity's deepest quests, understanding our cosmic origins and searching for cosmic company. They remind us that the universe's oldest light isn't just a relic of a mindless past. It's a medium that has carried the story of physics for 13.8 billion years. And if other stories are being written out there, stories of consciousness and civilization, this universal background might be the very page upon which they could one day be found. The silence of the cosmos, as heard through the cosmic microwave background, isn't empty. It's full of potential, a potential waiting for a signal, or perhaps for us to learn how to listen in an entirely new way. This data can feel overwhelming at first, all these maps and graphs, but you don't need a physics degree to start. There are tools now, whole suites of them, built to translate that ancient light into something we can sense. It's like learning a new language, but the alphabet is temperature and sound and color. The most famous image is the all-sky map, the cosmic microwave background. Usually shown in what's called a Malwade projection, it looks like a cosmic egg mottled with red and blue. The red areas are just a few thousandths of a degree warmer than average. The blue areas are slightly cooler, and it's not random. It's a precise map, a snapshot of the universe at 380,000 years old. To really see the scale, you can use interactive tools. NASA Eyes on the Solar System or the Planck Legacy Archive online. You can zoom, rotate, highlight different features. You see the plane of our own Milky Way, which has to be subtracted digitally to reveal the pristine cosmic signal underneath. It shows you the cleaning required, the work behind the data. One of the most intuitive ways is through sound. Several projects have sonified the cosmic microwave background. They take the temperature data from that all-sky map, assign a musical note to each pixel. Warmer spots get a higher pitch, cooler spots a lower one. Then a scanner moves across the map from one pole to the other, playing the notes in sequence. What you hear isn't noise, it's a chord, a deep, resonant hum with a distinct structure. It's the universe's fundamental note, with overtones from those acoustic oscillations. Listening to it, you are hearing the frozen music of the primordial plasma. It turns an abstract map into an auditory experience, makes the harmony of the early cosmos palpable. For the more analytical mind, the key is the power spectrum graph. This is the cosmic barcode. The horizontal axis is the angular size of fluctuations. Largest scales on the left, finest details on the right. The vertical axis shows the strength, the power of those fluctuations. The graph isn't a smooth line. It's a series of distinct peaks and valleys. That first tall peak at about 1 degree is the sound horizon at recombination. Its position tells us the universe is flat. The relative heights of the second and third peaks reveal the amounts of ordinary matter and dark matter. Interactive versions let you hover over each peak. See a pop-up explanation. It turns a complex plot into a step-by-step storybook, a list of cosmic ingredients. There's a hands-on demonstration with the CMB dipole. This is the largest anisotropy in the sky, but it's not primordial. It's caused by our own motion. Our solar system is moving relative to the rest frame of the CMB. About 600 kilometers per second, this creates a Doppler effect. In the direction we're heading, the microwave photons are blue-shifted. That region appears warmer. In the opposite direction, they are redshifted, appearing cooler. You can visualize this as a smooth gradient across the full sky map, a reminder that even our vantage point is in motion. Simple online simulations let you adjust a virtual velocity. Watch the dipole pattern change in real time. It's a direct lesson in relativity, written across the oldest light. By engaging with these tools, spinning the cosmic egg, listening to its hum, decoding its barcode, the data stops being a distant product. It becomes a personal discovery. You're not just being told about the universe's origins, you're given the instruments to explore them yourself. This is the bridge between raw data and public wonder, where the beauty of the cosmos meets the curiosity of the human mind. That faint glow from the beginning, that cold light, it's left the telescope behind. It's not just in the journals anymore, it's in our imagination now. The cosmic microwave background with its story and those mottled maps, it's a cultural touchstone. A symbol in novels and films for the deepest questions. In film, maybe the most poignant use is in Contact. The scientist Ellie Arroway, played by Jodie Foster, she's listening to the cosmos. Her quest is to find a pattern, a signal in all that cosmic noise, and the film's signal is fictional, but the backdrop of her search, that hiss, that's the real ancient radiation of the universe. The movie captures the emotional core of the pursuit, the hope that in the universe's natural static there might be a whisper of meaning, a connection. It frames the CMB not as data but as a canvas for our hopes and our loneliest questions. Writers have used it too. In Dan Brown's novel Origin, the cosmic microwave background is a key piece of evidence. For a character's grand theory about how we began, it serves as a modern relic, a scientific scripture holding cryptic truths. That use in fiction shows how the CMB has entered our vocabulary. It's a shorthand now, a shorthand for ultimate empirical mystery. It's replaced the burning bush or the sacred text with a data set, a different kind of revelation, but it carries the same weight. And then there's visual art, the most direct absorption. The all-sky maps from WMAP and Planck, with their fiery reds and deep blues showing the infant universe's temperature variations there in science museums and art galleries. They're celebrated not just for what they reveal, but for their beauty. These images are icons of a new creation story. They're our era's Sistine Chapel ceiling. A depiction of Genesis but painted by the laws of physics, rendered by satellite instrumentation. It provides a data-driven sublime, the same awe as a mythological birth, but its authority comes from measurement. From mathematics, it satisfies that need for a story of beginnings, now grounded in collective discovery. This fusion goes into music. The composer Baryon made a piece called The Music of the Spheres. It used data from the CMB's fluctuations to shape an ever-changing ambient soundscape. The universe's first structures dictate the harmony and the dissonance. It's a literal translation, the cosmic blueprint turned into art, blurring the line between scientific observation and aesthetic experience. It asks us to listen to the universe's first chord. Not as a metaphor, but as a composition. This cultural permeation, it tells us something. The oldest light does more than inform cosmology. It enriches our shared human narrative. It provides new imagery for old contemplations. Where we once looked to myth for creation stories, we can now look to a colorful map of temperature variations. A sonification of primordial sound waves. It connects the scientist's rigor with the poet's wonder. The cosmic microwave background has become more than a cosmic fossil. It's a modern cultural artifact, a testament that in seeking to understand the universe, we end up reflecting on our own place within it, and expressing that reflection in every medium we have. For a while, the origin of the universe was an open question. There were two main ideas. One was the Big Bang. It said the universe began in a hot, dense state. The other was the steady-state theory. People like Fred Hoyle supported it. In that model, the universe had no start and no end. It was eternal, and on the large scale, it didn't change. To explain why we see galaxies moving apart, the theory needed new matter. Just a few atoms here and there over centuries that would keep the density constant as space expanded. It was a beautiful idea, a cosmos that always was. Then came the cosmic microwave background. That discovery was a shock to the steady-state model. The theory didn't predict this radiation. In an eternal universe, there's no single hot beginning, no reason for a uniform afterglow, but Penzias and Wilson found it. This faint microwave signal was exactly what the Big Bang needed. The cooled remnant of an early fireball. The steady-state theory tried to explain it. They suggested maybe starlight was heated by dust, but that couldn't produce the perfect spectrum we see. That spectrum was the first key piece. The CMB's intensity follows a precise curve, a blackbody spectrum. It's the signature of something in thermal equilibrium. Like the glow inside an oven, the Big Bang naturally gives you that. The early universe was a dense, opaque plasma. It was in equilibrium. When it became transparent, that radiation was just released. And then it cooled as space expanded. For steady state to get a perfect blackbody across the whole sky, it would need a miracle. It would have to thermalize light from all different sources across all of time. Physicists saw that as virtually impossible. The second property was isotropy. The CMB is incredibly smooth, the same in every direction. In the Big Bang, that smoothness comes from the early hot state. Maybe helped by inflation later. In a steady-state universe, that smoothness is a deep mystery. Why would radiation from countless stars, created at random times over an infinite history, average out to perfect uniformity? The odds are vanishingly small. That smoothness pointed to a common origin, a single event that imprinted itself on everything we see. This moment became a classic paradigm shift. The CMB was the smoking gun. The Big Bang predicted it. The steady-state model did not, and it couldn't naturally fit it. The steady-state idea was philosophically appealing. But the data was clear. As we learned more about the CMB's details, consensus solidified around the Big Bang. It was a victory for evidence. The universe itself dictated the model, not our preferences. Other ideas fell to the same light, like the tired light hypothesis. It said redshift wasn't from expansion, but from photons losing energy over distance. That could mimic an expanding universe without a beginning, but it completely fails to explain the CMB. Why would that energy loss produce a perfect blackbody spectrum? And it can't explain the detailed pattern in the CMB, the hot and cold spots. That pattern is the fingerprint of sound waves in an expanding, cooling fluid. Only a dynamic universe with a hot, dense phase can produce that specific symphony. There's a lesson in this. Our current model, with inflation and dark matter and dark energy, is the champion because it fits the CMB data so precisely. But its victory over steady state is a reminder. All scientific models are provisional. They stand only as long as they withstand new evidence. The ancient light that cemented our story may still have anomalies. Things like the Hubble Tension or the cold spot, they could point to the next revolution. The cosmic microwave background isn't just a monument to a past triumph. It's an active testing ground, making sure our story of the cosmos stays faithful to the deepest whispers of reality.